In this presentation, we are going to focus on intermolecular bonding. We are going to look at the attraction between different molecules. We'll refer to this as IMAs, intermolecular attractions, and trying to understand how molecules of either the same type or even different types will start to interact and attract to one another, or maybe not attract to one another. To do that, though, we need to know what the character of a molecule would be. When I refer to character, I'm really referring to the polarity. So molecules might be nonpolar. A nonpolar molecule would be where there are literally no poles, which would mean there are no charges present. And the way you end up with no charges is the electrons that are being shared between atoms are evenly distributed. So there is no distinct positive or distinct negative area to the molecule. An example is depicted here, where we have chlorine. Chlorine is a diatomic molecule. We have two chlorine atoms connected to each other. They are both obviously from group 7. They're halogens. They both need one more electron, and so they're not going to exchange electrons, of course. They're going to share them. They share one pair. They both have the same electronegativity, 3.0, and so the pair of electrons being shared will be evenly distributed. There is no distinctly positive or distinctly negative area. That's a nonpolar molecule. That's its character. On the other hand, some molecules would be characterized as being polar. In a polar molecule, there is going to be an unequal distribution, and that is either going to arise because there's been an exchange of electrons, like in this ionic molecule here, sodium chloride. Sodium is metal, chlorine is a nonmetal. Sodium is an alkali metal, desperately wants to get rid of one valence electron, which it has done here, and it has passed it over to chlorine. Chlorine, again, is a halogen, would like to pick up one more electron to have an octet, and you can see it there. It has been transferred from the sodium over to the chlorine. Clearly not an even distribution. The sodium is got a deficiency of electrons, so it's got a positive charge, and the chlorine, now a chloride ion, has an extra electron, and it is distinctly negative. That would definitely be a polar molecule. Or polarity could arise from a covalent bond where there is enough of a difference in the electronegativities of the atoms that are bonded that they spend more time around one atom as opposed to the other atom in the bond. Here, seen in this water molecule, where oxygen has a high electronegativity, 3.5. Hydrogen, also a nonmetal, but its electronegativity is only 2.1. So both of these intramolecular bonds are polar covalent, and the electrons being shared, both pairs are spending more time around the oxygen end of the molecule and less time around the hydrogen end of the molecule. And so we have a distinctly negative area where the oxygen is, and a distinctly positive area where the hydrogens are. There are poles that exist, therefore this would be a polar molecule. And you can see the dipole moment drawn in on the right side, the arrow pointing towards the oxygen. That's what we mean by character, the polarity. Is it nonpolar or is it polar? Now, the polarity of the bond then helps to decide whether there is what we call a dipole moment. And a dipole moment, you're looking at the entire molecule. We're not looking just at the polarity of individual parts of the molecule, the individual atoms. We're looking at the entire molecule, and we're looking at whether there really is across the entire molecule an uneven distribution. So if we have a dipole moment, that will determine whether there really is a polarity to the entire molecule, and therefore we would characterize it as being polar. On the other hand, the individual bonds might be polarized, but because of the geometry, there may be a canceling out, and the effect ends up being no pole existing, and therefore no dipole moment being present. So if you can have a dipole moment, if one exists, then that would just determine whether you have a polar molecule. So we have to weigh in with the geometry, not just the individual bonds and whether there's an even or uneven distribution, but we got to look at the geometry and see if there is sort of this canceling effect. I think if you see the examples I'm going to give, it will make more sense. So let's look at a situation where I have individual bonds are polar, but there ends up not being a dipole moment. In this first example, I've got a carbon dioxide molecule. Carbon is doubly bonded to two different oxygens. That's what the double line means. Oxygen has a much higher electronegativity, 3.5, as compared to carbon, which is only 2.5. So the oxygens are attracting the two pairs of electrons they're sharing with the carbon, so that the electrons are floating out and spending more time around the oxygens. I'm depicting that effect with the arrows. So the arrows point towards the more electronegative element. They point away from the less electronegative element. Notice the arrow, then I put a tail on it, and it looks like a plus sign, because the carbon is going to be a little deficient. It'll be a little bit positive. Well, if you imagine these arrows represent, let's say, forces. And so if I had two forces acting on an object, the carbon, and they're acting in complete opposition to each other, and they are equal in size, they would tend to cancel each other out. And if carbon were an object, that object wouldn't move. There is no dipole moment here. So even though the individual bonds were polar, because of the geometry, it being linear, molecules can have polar bonds, but the geometry may dictate that a dipole moment does not exist. The vectors cancel out. Let's look at another example. Here you have boron trichloride. You can see the geometry is trigonal planar. We know those angles between the bonds are 120 degrees. Again, all three bonds are polar covalent. And so if you imagine three people pulling on a central object, they're of equal magnitude, they're equally spaced. If B were an object, it's not going anywhere. The geometry would cause those three vectors to cancel out. There would be no dipole moment. And so even though both of these molecules have polar bonds, the geometry was such that the dipole moment does not exist. The vectors cancel out. So you need to know the geometry. At this juncture, you don't know how to derive geometries on your own. It would have to be provided to you. On the other hand, of course, there can be polar bonds, and the vectors do not cancel out, and a dipole moment does evolve. And so if we go back to water that we looked at a little while ago, the three atoms are not collinear. They're at an angle to each other. That angle is 104.5 degrees. Again, you wouldn't know that at this juncture, but take my word for it. Oxygen is more electronegative than hydrogen, so my dipoles of the bonds point towards the more electronegative element, the oxygen. The hydrogens are slightly positive. Again, the tail looks like a plus sign. So if those were two people pushing on an object with equal force, the object will start to move and it would move upward. And that larger arrow shows you the net effect. And so that's the direction of the dipole moment. So one, it did evolve. The individual bonds were polar and the molecule is also polar. Same thing with here, nitrogen trifluoride. This is a trigonal pyramid, so that nitrogen is sitting at the apex of a pyramid. The fluorines are much more electronegative than the nitrogen, so the arrows point down towards each fluorine. So imagine that nitrogen is hovering above the fluorines. If this were depicting three people pulling with equal force downward on that object, of course, it's going to move downward, and you can see to the far right, the dipole moment points directly downward, and therefore there is a dipole moment, therefore this is polar. So the geometry was such that the polarity of the individual bonds did not cancel out, and so a dipole moment exists, and if one exists, we characterize the entire molecule as being polar. If we put these molecules now into an electrical field, if they've got a dipole, which is what it means when they're polar, then they should interact with the electrical field and they will be attracted by the positive and negative plates. And here you see some molecule with the red end of the molecules are positive, the blue end are negative. The two plates are labeled as positive and negative, and so they align themselves. They opposites attract, and the negative ends of the molecules are being attracted by the right-hand positive plate. The positive end of the molecules, the red ones, are attracted towards the negative left-handed plate. So they would actually respond to the electrical field. All right, so now once we know the character of the molecules, now we can actually talk about IMAs, intermolecular attractions. So again, remember, literally that means the attraction between molecules, not within the molecule, but between them. To understand what the attraction would be, we need to know what the character of the individual molecules are. Are they polar or nonpolar? And as we've just seen in the examples I've discussed, that's determined both by the intramolecular bonds, which is, of course, the electronegativity chart, helps us with that evaluation, and the geometry. All right, so anyways, there are three different IMAs. And the first one is called dipole-dipole. Now, before we even look at the specifics of what dipole-dipole means, let's take the term, a dipole. Well, literally that means two poles. So that tells you out of the box that you have to have molecules that have polarity. They've got to be polar molecules. So if you have nonpolar molecules, there won't be a dipole-dipole interaction. So dipole would mean that there is a positive and a negative end to the molecules. So this sounds a lot like electrostatic attraction. Opposites attract. And you see that happening in this diagram. This diagram is depicting a handful of molecules, and you can see that on those molecules I've put the partial charges. One end is slightly positive, one end is slightly negative. And so adjacent molecules, opposites will attract. The positive ends of one molecule will attract the negative ends of adjacent molecules. So whatever neighbors are surrounding an individual molecule, we can have an electrostatic attraction. We can also have electrostatic repulsion. So you can see the larger arrows, the black arrows, show where like charges would also repel. So you've got sort of this balance between attractions and repulsions occurring. But those are dipole-dipole attractions. That's a particular IMA. So you see it readily that it exists here because the individual molecules were dipoles, they were polar. Yes, they will interact. Hydrogen chloride, offering up a different example. Here you see on the right side a handful of hydrogen chloride or hydrochloric acid molecules. On the left side, actually writing the detailed atoms, and of course they're not sharing electrons equally. Chlorine's more electronegative, so the chlorine end of the molecules are slightly negative. The hydrogen end of the molecules are slightly positive. So we've got polar molecules, we're going to have dipole-dipole interactions. These are very strong. Not the strongest, but very strong. It is more difficult to pull apart molecules that have dipole-dipole attractions. All right, so that's the first kind of IMA, dipole-dipole. Now, closely related to that, and actually a subcategory of dipole-dipole, are attractions called hydrogen bonds. And hydrogen bonds I'll depict here with two different diagrams. The left-hand diagram is water interacting with ethanol, and the right-hand molecule, water molecules interspersed with formaldehyde molecules, and they look like they're forming bridges between each other. All right, so here are the criteria. Hydrogen bonds actually have criteria that have to be met before they possibly will exist between the molecules. Well, number one, obviously, you got to have hydrogen atoms within the molecules we're discussing. But second, you got to have those hydrogen atoms connected to other elements that have a really high electronegativity. And we know the highest electronegativities are found in the upper right-hand corner of the electronegativity chart. And the three that we're going to focus on, nitrogen, oxygen, and fluorine. If they're bonded to hydrogens, they're going to tend to leave the hydrogens a bit deficient in electrons. If hydrogen is a bit deficient, it's going to want to make that up. The hydrogens want to be stable. So they will look around in their environment to adjacent molecules. So now remember, these are IMAs, intermolecular, not within the molecule, but between two different molecules. So the hydrogen will look to its neighbors, and the third criteria, it's seeking out lone pairs, electrons that would be on atoms of different molecules that are available to be hooked up with. And in both my diagrams, I'm depicting the hydrogen bonds with a dashed line. So you can see in the left-hand diagram, the water molecule, the hydrogen on the water molecule is a bit deficient because it was hooked up to oxygen, right, in that water molecule. And it looks to a neighboring ethanol molecule, and it sees the lone pairs on the hydroxyl group of a different molecule, and it bridges to that. And again, I'm distinguishing it from an ordinary intramolecular bond, the covalent bond, by drawing it in a dashed fashion. And you see several of those dashed lines in the right-hand diagram also, as these bridgings between different molecules is taking place. Hydrogen bonds, very strong. These are the strongest of the IMAs. They actually are a variation of dipole-dipole. Very important. Going to hear a lot about hydrogen bonding in the days ahead, not only in this class, but particularly in biology. There is a third type of IMA, and those are called dispersion forces, or sometimes referred to as London dispersion forces. And in these, they too are sort of a variation of dipole-dipole, but they're evolving because of what we call intermittent dipoles. The electrons in atoms are, in molecules and between atoms, are always orbiting. And at any given moment, they can be concentrated on one atom as opposed to a different atom. And at any given moment, then a particular atom would have an excess of electrons and be a little bit negative. And if they've moved away from a different atom, there's going to be a little bit of deficiency. But in, again, another moment, they will orbit back to the alternate atom. And so these positive and negative charges kind of keep flip-flopping continually, and so they exist, but not for for any length of time. And so really what happens is it's a kind of low-grade dipole-dipole interaction, electrostatic attraction. I like the right-hand diagram here because here are a bunch of what we call hexane molecules. You can see they're made up of carbons linked together in a chain, and then a bunch of hydrogens that are connected to it. All of those bonds, the carbon-carbon and the carbon-hydrogen bonds, are pure covalent bonds. So there are no dipoles, all right? So there can't be dipole-dipole interaction. There can't be hydrogen bonding. There are hydrogens, but they're only connected to carbons, so no hydrogen bonding. So what would attract them to each other? Hexane is a liquid. There must be some attraction, and it's this very low-grade electrostatic attraction. I'm depicting it like with these green lines, trying to communicate to you that there is some attraction, but they're going to be very, very weak. This particular IMA dispersion forces are incredibly weak. It would be easy to pull apart the hexane molecules. Hexane has a very low boiling point. If I had a container that was holding hexane in it, like a beaker, and I set it out in the lab, you would be able to smell it throughout the room because it would be evaporating very, very readily because of the very weak dispersion forces. Now, if you've got a nonpolar molecule, this is it. This is the only kind of IMA that could exist between nonpolar molecules. But all molecules will have some dispersion forces. The thing is, with polar molecules, dispersion forces aren't going to be a big factor, not compared to both dipole-dipole and hydrogen bonding possibly existing. But you have to acknowledge them. They can have an impact. You'll see that when you do a lab on evaporation, we can illustrate this impact. Now the thing is, even though they're weak, if the molecules start to get bigger and bigger and bigger, there are more and more atoms that have these intermittent dipoles, these short-lived dipoles, so they can start to accrue. The molecules get bigger and bigger, the attraction gets more substantial, and you could have some nonpolar substances that not only are liquids, but some of them could even form solids, albeit they would have low melting points. So those are the three kinds of IMAs. You've got dipole-dipole, hydrogen bonding, and dispersion forces. We'll be talking about these a lot in the coming days. Now, one last thing I want to consider before we wrap up here. Some molecules are what we would refer to as mixed. Here is an ethanol molecule. You've run into this before in a couple different labs. And if we analyze this, if you look to the right end of this molecule where you have that hydroxyl group, you know that those two bonds over to the right, the carbon-oxygen and the oxygen-hydrogen bonds, are polar. So that end of the molecule would be polar. However, to the left side where you've got the two carbons connected to each other, and then the carbons subsequently connected to hydrogen atoms over here on the left, we know that those are pure covalent bonds, and we know that end of the molecule is nonpolar. So I would refer to this as a mixed molecule where there's a relatively polar end to the right and a relatively nonpolar area to the left. They're about equal in size, so neither one is dominating. I probably would just refer to this as a mixed molecule. Neither one is dominant. However, when one or the other characteristic of a mixed molecule starts to dominate, like you see in these two molecules where they've got this huge chain of carbon atoms, on both of them, on the far right side, we have what are called carboxyl groups, both of them. And again, you've got carbon-oxygen and oxygen-hydrogen bonds, which are polar covalent. That small portion of both molecules is polar. But on the left-hand side, you've got these long chains of carbons connected to one another, and then the rest of the bonds are taken up with hydrogen atoms. these are definitely nonpolar or pure covalent bonds. Those long tails are nonpolar in character. So even though these are mixed, they are predominantly nonpolar. So I would characterize these as mixed, and then I would write, maybe in parentheses next to the name, I would write nonpolar to remind me which character dominated. So that's a little trick I use to help me know that if I start to mix different molecules, what's the potential of there being an attraction between them. We'll revisit this later on. There's a lab where we will actually mix different molecules and try to make a judgment about whether they would be attracted to each other or not. So those are IMAs. You need to know what's the character of the molecules, and from there you can evaluate, do we have dipole-dipole interaction, do we have hydrogen bonds, or do we merely have dispersion forces?